So in this video, I'm going to show how to calculate derivatives using spectral methods through the ComFiT library, and I'm going to do it in three ways. So first, instrumentally show you how to do it technically, and then I'm going to give a hand-wavy, less technical explanation for how it works, and then finally, I'm going to go into more of the details behind a discrete Fourier transform and see why it works. So I've installed ComFiT. Next, I'm going to import these packages, ComFiT and NumPy. And the function that we're going to calculate the derivative of is this function here, g of x, which I have coded here. So I've created an instance of the base system class and then calculated this function, and you can see that it looks like this. So to calculate the derivative of this function, the first thing that I'm going to do is to calculate the Fourier transform of the g function. So I'm going to call that gf, and I just realized that I need the SciPy package to do so. So I'm going to import the SciPy package as well. You can use NumPy, but I've found that SciPy is slightly faster in some circumstances. So this is me transforming the g function. So now I'm getting the Fourier transform of that. And then I'm going to multiply gf with the kx vector, the k vector. So I'm going to get, I'm going to write dx of g in Fourier space as 1j. This is the imaginary unit times sys dot k of 0. That's where the k vector is stored. And then multiply with gf. And that creates the derivative of g in Fourier space. And then to get g, the derivative back, I'm going to do an inverse Fourier transform. So .fft, that's where it's located, EFFTN of dxgf. And whenever you do this, you typically pick up some imaginary part as well. So since I know that g is a real function, I'm also going to take the real part in the end, like this. So now I've calculated the derivative of g, and to show you that it works, I'm going to plot the function. So sys.plot field. Oh, sorry, I forgot. This should be dxg, and this should be dxg as well. dxg, and you can see that we get the derivative of this function here. So when the function is increasing, the derivative is positive, and then it turns negative as it's descending, and so forth. And notice that this function here satisfies the periodic boundary conditions, which is a prerequisite to use ComFiT. So that's how you do it. Now over to the second part, which is the more hand-wavy explanation for how it works. Essentially, what we're using is the properties of the Fourier transform. So for an infinite system, the Fourier transform is given like this, right? So you have this integral over all space multiplied by e to the minus ikx, and then this normalization factor. And the inverse Fourier transform is given by the same expression with other 2 pi and then ikx in addition. And now if you just take the derivative of this function g, you see that this derivative operator, the dx here, it doesn't really care about the integral because the integral is an integral over k. And inside the integrand, the only thing that is really a function of x is this exponential factor here. And when I take the derivative, I get down this ik factor, which I can put together with gf here. And so the idea then is that in order to get the derivative of the function, I take the Fourier transform of the field, that is gf, I multiply by ik, right? So that gives me this thing here. And then I just do the inverse Fourier transform of that resulting bit, which is this function here. And that should give me dxg in return. So you can see that's what I did here. So I calculated Fourier transform of g, I multiplied by I times k, and then I took the inverse Fourier transform of that, and then I took the real part. So that's the hand-wavy explanation. Of course, the more third part of this, the more technical explanation, is that we are in fact working with a function that is defined on discrete points in a on a periodic lattice, right? So we have a function g of xn, which is defined on n points, x0, x1, all up to xn minus 1. And the discrete Fourier transform of this function is given by this equation here. So we have the mth component of the resulting Fourier transform is going to be this g sum over all the x points, and then the function evaluated at those points multiplied by this exponential factor here, which have both m and n in the exponent. Now, in order to see how we get from here to the derivative, we're going to see that this xn point here is related to this n value, since the xn value is the 0th x value plus n times delta x, where delta x is the step length in the function. And so I can rearrange this equation to get n as a function of xn and x0 and delta x. And then if I insert that instead of n into this Fourier transform, then I get the following expression, where you can see that I have the sum over all the xn points, g of xn, and then the exponent factor now with something as a function of m multiplied by xn minus x0. And if I define now these k values, this km, where m goes from 0 to n minus 1, of 2 pi m over n delta x, that is everything that is not multiplied by xn minus x0, then you can see that I can replace this 2 pi m over n delta x with km. And so now my this discrete Fourier transform looks like gfm, the mth component, is the g of xn multiplied by the exponent of minus ikm xn minus x0, which now looks a lot more like the can I delete this? Which now looks a lot more like the Fourier transform in infinite space, right? Because I've written it in terms of the wave number explicitly. So this k here is called a wave number. Now, if I look at the inverse discrete Fourier transform in terms of this k here, it looks like this. So I can get back the value of g evaluated at xn by the summation from m equals 0 to n minus 1. So here I'm summing over the km values instead. And now you can see that if I now multiply this expression here, what I have inside the expression, so if I multiply this gfm with ikm, as I did in the in the code, then you see that I get this right-hand side becomes this thing where I have ikm gfm multiply this by this exponent. And the important part here is that if you're looking at this expression, so here I have g of xn, it's the function of some function evaluated at a point xn, and if and it's a sum of coefficients multiplied by these exponent functions. But of course, if I have a sum of functions and then I replace each of those functions in the sum by the corresponding derivatives, then I should get back the derivative of the function on the left, because the differentiation is a linear operation. So what I have then is that I can argue that if I multiply by ikm, then I just get back the derivative of g evaluated at xn. So it should be xn here. So that's one way to look at it. A different way to look at it is to say that instead of looking at this as a sum over functions and replacing each of the functions by the derivative, I can also think about it as if I'm differentiating with respect to xn. So if I differentiate with respect to xn into this sum here, then you can see that the only thing that's really a function of xn is this exponential, and then I just get this ikm factored down as before. I don't know. To me, it doesn't really make sense to think about differentiating with respect to sort of prescribed points. So choose whichever explanation you like. And so, so that means that in order to calculate the derivative, as I did in this expression here, I need to be able to have access to these k vectors here, which are these k vectors here, and that is exactly what the calc wavenom function in ComFiT is doing. So just to show you, if I print the value of gf, so the Fourier transform of f that I calculated, you can see that it contains a list or an array of all the coefficients gfm, and then the km, the sys.k0 has been calculated using the calc wavenum function upon the initialization of the instance, and it contains the wave numbers km, so k0, k1, k2, k3, k4, etc. So when I'm multiplying k0 times the Fourier transform of f, and also with one j, so the I in Python is j, then I get this thing here, which is what I'm putting inside here before doing the inverse Fourier transform to get back the derivative of the function. Now, as I say, this is what the calc wavenums function is doing, which is found in the base system class and is called during the initialization of the instance. So it's calculating that. There's a small caveat, which is that in fact you can see that it has these limits on high and low. So it finds n as the length of whatever position vector you're inserting into it, and then it's calculating the high, something called high and low, which is used to calculate these wave numbers. And here you can see the 2 pi divided by L. So L is n times dx, right? So if you go back to the expression, we see that km is 2 pi, and then this number m divided by n times delta x. That is exactly what we have here, except that instead of km going from 0 to n minus 1, we see that m is going from 0 to n minus 1 divided by 2, and then from that point on, from minus n over 2 to minus 1. And the reason is that when we're working with a function that has a discrete points in space and we're doing the discrete Fourier transform, we can't really make sense of all the wave numbers in terms of this ever increasing km quantity here. And the reason has to do with the Nyquist theorem, which says something about which frequencies are you allowed to make sense of when you're doing a Fourier transform. So that's very briefly put, but it says that you can only sample a signal up to a frequency of 1 over 2 divided by delta x, where this is the distance between the x points. The corresponding wave number to that frequency is found by multiplying with 2 pi. So I multiply this expression with 2 pi, and then I get pi over delta x. And so the value of m, which corresponds to this Nyquist frequency, or the Nyquist wave number, if you like, the k, is found by equating the expression for m to this here, and we find m equal to n over 2, which means that for this 0 to, for the values of m from 0 to n minus n over 2, then these values of the wave number make sense, but beyond that we have to do something else. And as a matter of fact, for the higher values of m, the ones that are greater than n over 2, they actually correspond to negative wave numbers. And to see that, we can see what happens when we insert a negative wave number into the Fourier transform. So here, if I insert minus km, where km is a wave number that is smaller than the Nyquist wave number here, into the Fourier transform, then I get what you could call gf of minus m, or g of minus km. And I just insert the negative wave number here. And what I will argue now is that this is actually the same as looking at a wave number that is beyond the Nyquist wave number, but not up to 2, not all the way up to 2 times that. So I'm going to argue that this is the same as looking at the component that corresponds to 2k nq minus km. And the way to see that is that if I insert the definition of the Nyquist wave number into this pure exponential function, so I've just look at the, imagine that I expanded this exponential in 2 factors. So first the exponential with the 2k and q, and then the one that I have here. Then the part that has 2 and q in it is just 1, because if I insert the Nyquist wave number, pi over delta x, then you can see that I get minus I and then 2 pi over delta x. And xn minus x0 is an integer, or there's several ways to look at it. So I could say that if you go back to the, the definition of n, here you see that xn minus x0 divided by delta x is n, which is an integer. And so essentially what I have here is an exponential xn minus x0 divided by delta x, that's an integer, and then I multiply by 2 pi, that's an integer of 2 pi, which means that essentially I have just 1. Which means that finding that the Fourier component of this frequency here, this wave number here, which is above the Nyquist wave number, but not as high as 2 times that, is exactly the same as what would be the wave number of a negative wave number. So this has to do with the fact that when you are sampling a signal and you're using too high, and you're sampling a high frequency, and you're sampling with a high frequency, you sometimes could get aliasing, and for the discrete Fourier transform, it works out that it works out the way that for values larger than n over 2, then you can interpret those as being negative wave numbers. So that's what's happening in this second part of this wave number function. Yes, so this is why we first set the n half k values to be just those, so 0 to n over 2 times this factor, and then the following wave numbers to this. So if I now print the k numbers here, you can see that the first wave numbers 0 all are positive and increasing all the way until this wave number here, which then turns negative, and then you just get the negative values increasing up to the mirror image of that. So that was the 3 explanations of how to compute derivatives with spectral methods. First, just instrumentally how to do it with the ComFiT library, and then like a high hand-wavy explanation using the infinite Fourier transform, and then the more technical explanation which has to do with how the discrete Fourier transform works and the Nyquist theorem and all of that. And I encourage anyone who's more interested to look into sampling theory and the Nyquist theorem to get a better sense of this. So thank you.